Today I'd like to show or prove this result from real analysis, which is I think is pretty intuitive, but also really interesting proof, I think, and it kind of helps you understand all this weird integrability stuff about functions. And this is specifically from chapter 8 of J. Cummings' Real Analysis. I've adapted the proof a little bit to make it easier. I'm not going to write down all the details, but you should be able to fill them in. So basically this is saying that f is a function from the closed interval a to b to the real numbers, and if p is a partition of this interval, then the lower sum of the partition is less than or equal to the upper sum of the partition in the function. So basically, let's just say this partition is, let p equal, it'll be, we don't even have to say it's equal, it's just p will be some partition x sub I minus 1 to x sub I, and of be a partition p of a to b. Clearly, so we know that m sub k will be the infimum over the interval, and m sub k will be the infimum, or the supremum over the interval. So infimum and supremum, and these will be kind of the heights of the rectangles that you choose. And basically, it's clear, since this is the infimum and this is the supremum, there's a result that says that the infimum is less than or equal to the supremum of the set, and the set is this, and they're both over the same interval, so clearly m sub k is less than or equal to capital M sub k, which means that using our definitions of the lower sum and the upper sum, L of fp equals the sum from I equals 1 to n of m sub I times x sub I minus x sub I minus 1. Clearly, that's less than the same thing multiplied by capital M sub k, since these are less than or equal to each other. So clearly, that's less than the same sum, I equals 1 to n of capital M sub I, of x sub I minus x sub I minus 1. And what's this? That is just u of fp. So we've proven this first part. Now we're going to prove the second. So for b, say to prove b, we want to show that for any two partitions of a to b, then L of fp1 is less than or equal to u of fp2. That's basically what we're trying to show. So basically that the lower sum of any partition will be less than or equal to the upper sum of any partition. So to do this, the idea is kind of to find something to, like, I'm going to get rid of that for a second, something, let's say like star, to like squish between them so that we can show these are less than or equal to each other. So that's what we're trying to show. The way to do this, or one way to do this that I'm going to show, is using the idea of refinements, which is, it's a pretty simple idea. It's that you take a partition, and then, so let's say a partition P, and then a refinement Q is that partition plus some amount of points that makes the approximation of the area better. So basically P is a subset of Q. Has to be. So, with this kind of loose definition of refinements, we can see, let's say Q is equal to the union of P1 and P2. That means that Q refines P1 and P2. Why is this? So Q refines P1 because, well, as you can see, P1, the union of P1 and P2, P1 is a subset of that. So, and you're adding more points. I mean, not necessarily adding, you're either adding or keeping it the same. So, you're refining it. And same thing for P2. So, with that, we can say, kind of with this fact about refinements, we know that for the lower sum, L of any partition P1 is less than Q, L of FQ, because it's refining that area, it's adding more points. And then we can say that upper of FP2, some partition P2, is greater than or equal to U of FQ. Boom. With that, we've essentially almost proven this whole thing. So to prove this, to solidify this, we're going to recall from actually the first part of this proposition that we proved, L of FP for some partition is less than or equal to U of F of the same partition P. So with that, this partition is the same as this partition, so clearly L of FQ is less than or equal to U of FQ. But then we know that L of FP1, lower of the partition P1, it's going to have to be squished a little bit, is less than or equal to the lower sum of the refinement. And then we know that the upper sum of this partition P2 is greater than or equal to the upper sum of the refinement Q. So we get U of FP2. So what have we shown here? That's the result. L of FP1 is less than or equal to U of FP2, which should make some intuitive sense because obviously the lower sum is always going to be, let's say we have this interval, the lower sum is always going to be kind of below this curve, and the upper sum is always going to be above it no matter what you have. So the upper sum's always going to be greater than or equal to the lower sum. Okay, I hope you enjoyed this video, and let me know if you'd like to see more of this real analysis content. Thank you for watching. Bye.